Yeah, the coefficient matrix is exactly it. Let's see here. Here, let me look at a specific one here. Suppose we're looking at, for example, we could be looking at t of x, y, z equal to 2x minus 2y plus 2z. All right, x minus z, and for my third component, 2x minus 3y plus 2z. All right, so you guys can tell me what the standard matrix is here. That's not a big deal, right? 2 minus 2, 2, 1, 0, minus 1, 2, minus 3, 2, right? So that's the standard matrix of T. And we got x, y, z. All right. Excuse me. So I want to explain to you what's the matrix of T look like in the beta coordinate system. I think I'll call it beta bar actually. Beta bar, just to make sure it aligns with my notes. I'm actually looking at example 5.4.17 on page 160. And so the basis, the non-standard basis we're looking at is 1, 0, 1, 0, 1, 1. Or did I say 0, 1, 1? I said 0, 1, 1, didn't I? And 4, 3, 1. So suppose you use that as your basis. What would the matrix of T look like with respect to that choice of basis? All right. So I want to derive for you like a sort of the analog of this form. So this formula is super nice for finding coordinates for a non-standard basis for column vectors. Okay. I want to derive the analog of this for linear transformations. We're going to find out it's really, really similar. Let me just kind of go through the argument with you. So we've got Rn. We have our linear transformation T. Go to the other copy of Rn. I've got my coordinate transformation phi beta bar. My coordinate transformation phi beta bar. Down here, Rn. Down here, Rn. I'm thinking of these as being the coordinate vectors. And so down here, we do multiplication by the T beta bar matrix. Now, it's helpful, for me at least, to rewrite that as, so like we have this notation, L sub A of V is equal to A times V. So this is the linear transformation induced by A. So with that notation, I can express this by saying L of T beta bar is equal to, I can look at these mappings and view it in terms of composition of mapping. So like this mapping here is the same as doing like this. Like that. So let's see here. Basically that is phi beta bar composed with T, composed with phi beta bar inverse. Oh, man. Oh. But the thing is, since this is a linear transformation from Rn to Rn, I can also write that, this I can also write as the multiplication of just the standard matrix T. Let's see here. So, so anyway, long story short here, this gives us that the standard matrix, not the standard matrix, the non-standard matrix T beta beta is equal to the standard matrix of phi beta bar times the standard matrix of T times the standard matrix of phi beta bar inverse. So I won't belabor this point, but that follows. And this right here, if I put this in terms of the coordinate mapping, this actually says that the phi beta acting on x is equal to beta inverse times x. What does that say? That says that the standard matrix of the coordinate mapping is just what? What's the standard? If the phi beta coordinates is multiplication by beta inverse times x, that means that the standard matrix of phi beta is just beta inverse. Just like over here, T times vector, all right, T of vector is this matrix times vector. That makes this matrix the standard matrix of T. I'm merely saying the same thing for the coordinate mapping over here. Phi beta acting on x is this matrix times x. That makes this matrix the standard matrix of the coordinate mapping. So I just put that over here, and that gives me beta bar inverse T, and then beta bar itself, because there's a theorem that says that the matrix of the inverse transformation is the inverse of the transformations matrix, yeah. Like I'm using a theorem here that the matrix of T inverse is actually equal to the matrix of T inverse. And it doesn't sound like I'm saying anything, but the matrix of T inverse is the matrix of T inverse. Sorry, English lets us down here. See what I'm saying? The matrix of the inverse mapping is the inverse of the matrix of the mapping. And this right here, guys, is all you need to really know. This is the takeaway message here, is to find the linear transformation, the matrix of the linear transformation with respect to a non-standard basis. We just have to multiply it before and after by the inverse of the basis matrix times the basis matrix again, like that. So, what's that? An example would be helpful. I have one right here. Now, this is the one I want to do with respect to this, right? But, so like beta, no! Beta bar 1, 0, 1, 0, 1, 1, 4, 3, 1. So what's beta bar inverse? I don't know, I can't do it in my head. I mean, it's a 3 by 3 matrix. Inverting a 3 by 3 matrix is calculationally intense, right? But I have the details worked out over here. If I can get it to work again. Oh, here it is. So what
What is phi, like represent?
Phi is the coordinate mapping.
Okay, thank you.
Basically I have two notations for it. Come on. Come on. You can, come on, off there. So the thing is, I have this is equal to this. This is a nice notation when I'm thinking about a vector and I just want to say these are the coordinates of the vector, right? This is helpful to me when I'm trying to understand the relationship between the linear transformation and other things, because it involves looking at maps composed with maps. So having a mapping notation for it is helpful when we're trying to like derive this, then this, and then here's the takeaway message, is that the matrix of a linear transformation with respect to a non-standard basis is just given by, this is called a similarity transformation. It's multiplication by the inverse of the basis matrix, the standard matrix, and then the transformation again. Now, a lot of people use P, like basically P is just equal to the basis matrix, okay guys? Which in this context would be beta bar, because that's what I said. But, excuse me. So there's the, oh, what's going on here? Yeah, sorry, I'm an idiot. So there's the basis matrix. It's not obvious, but that's the inverse of it. You'd have to do a calculation to figure that out, right? It's an inverse of a 3 by 3. We can do it though, right? There it is. It's not at all obvious that, I mean, it's a calculation that I'm not showing you at the moment, because we don't have enough time. And because it's not interesting, we've already done it earlier in the course. So there's the inverse matrix. And here's the standard matrix. We've just worked that out a second ago. And you multiply these three things. You guys can multiply products of three. Some of you balked at the process of multiplying three matrices on the test. No. This is something you can do. Multiplying three matrices is not too bad. You can do it. You just do 2 and then do it again. So this times this gives me that, and then this times this gives me that. Whoa. And that's interesting, right? So check it out. We start with this rather complicated matrix, right? And then by multiplying, making this rather special change of basis, this is our new matrix. This is really what we're after. We want to find a way to simplify formulas for linear transformations by making a good choice of basis. This is ultimately our goal, right? Otherwise, this is just a bunch of fun math trivia, you know? But there's a purpose to here. And so in these x bar, y bar, z bar coordinates, the formula for t of x bar, y bar, z bar, so to speak, is just 4 times x bar minus y bar, z bar, which is like way simpler than t of x, y, z, which is 2x minus 2y plus 2z, x minus z, 2x minus 3y plus 2z, right? Like you can easily see what the nature of the linear transformation is from this formula. This formula is uncoupled, whereas the original one was coupled, right? What do you, have you guys looked at the syllabus? I'm just kidding. I know you guys haven't looked at the syllabus. I mean, I've barely looked at the syllabus, and I understand. Who wants to look at the syllabus? But these kind of vectors are actually what are called eigenvectors. So this is actually an eigenbasis, and we're doing a similarity transformation with respect to an eigenbasis, and this is called diagonalizing this matrix. We're doing a similarity transformation on the matrix and turning it into a diagonal matrix. So I will spend considerable time in here trying to explain to you why this is interesting and useful. But sort of the backdrop of it, it's I mean, I know it's confusing. It's this stuff. I mean, this way of thinking is what explains this formula. And so this formula you need to know and understand. We'll talk more about this. Anyway, so next time, if you guys have questions about the recommended homework in Chapter 3, please ask them. We should have time for some of those. And then I will quickly, pretty soon go on to geometry and other things. The things we're talking about are now basis, coordinate, vector spaces, transformations, matrices, transformations. These things will continue to be with us. So it's not like I'm going to leave them behind. It's just they become more interesting as we go on and study the future chapters. So we'll continue to reinforce these ideas while introducing the new and more interesting ones, which we're actually actually more after. To me, a lot of the problems in chapter 3 kind of seem artificial for you guys, because we're trying to look at applications, right? So it's hard to find an interesting problem in chapter 3, which is really an applications problem. I do think Shore does a good job where he shows you how to rotate coordinates to make the formula for a certain thing nice. So I might go over that next time if I remember. But I probably spent too long talking about the test today. Sorry about that. But I thought you would appreciate it if I did. So I'll shut up. Have a good weekend. I think maybe I'll be better next time. I actually have a cold at the moment.
Is the missions grade going to be up soon?
Missions grade? They're not up? No. Oh, yeah, the grader just asked me for the... It should be up today, I think, if I get it from him. And did I give them back to you yet?
Huh?
I didn't give them back to you yet, did I? The missions, I haven't returned them yet.
No.
I